we talked about on Tuesday, we talked about the beginning of loop invariance. Loop invariant is valid only if the loop body actually maintains the property, i.e. the loop invariant remains true at the end of each execution of the loop body. That is this part right here, the end of the execution of each loop body. To show this, you have to assume that the loop invariant is valid at the start of the loop. So here, as well as the loop condition is true, which means that you will actually enter the loop. And because we did not change it, it will be true here. So it's a lot of assuming that something is going to be true because it was true before. And because it was true before, it's true after, and it's true elsewhere. It's a lot of mathematical induction with, it's like inception, basically. So to show that the loop invariant is true at this red point, you assume that the invariant is true at this green point, and you can assume that it's true at the green point because demonstrably, it should have been true at the beginning before the while loop was tested. And since we don't change anything in the test condition, it should be true here, which means it should be true here, which means it should be true there, which means it should be true there, so on and so forth. Okay, to justify the assumption that the loop invariant holds true just after the loop condition tests, right here, we say that's true because the loop invariant holds just before the test and because we don't change anything during the test. This is not circular reasoning or I guess it would be like an Ouroboros, the snake that eats its own tail, but rather mathematical induction, which is a confidence building approach, similar to how we use with recursive methods, proving that it worked on the smallest case. So if you can prove that it works just before the loop condition starts, then you can prove that it works right after the test condition, which means you can prove it'll be true at the end of the condition, which means you can be true at the beginning of the condition again. So it has to be true at the green point on the first iteration, and then it has to be true on the second iteration, and then the third iteration. And eventually you get to the point where at the end of the kth iteration, it must be true at the end of the k+1th, or the start of the k+1th iteration. Because again, we never change anything within the testing condition. Okay. And since it's true at this point, and then the testing condition doesn't change anything again, it must be true after. So those are the 4 points there. It's a lot of you assume, or you can assume, that it's true at some point because it was true at another point and we didn't change anything about it. And that's how you get to all 4 corners of the loop invariant world. Okay, here is the second example. If you remember, we had another example. It was the Q one, where you took elements from one Q and appended them onto another. And the loop invariant that we came up with was that all of the elements remain the same and are in the same order and always maintain the same length, because otherwise you would lose items. So we have our second example here, which is the power method. Returns a double, takes in a double x and an integer p, and returns x to the power p. Requires that p is greater than 0, ensures that the power is equal to x to the power of p, wherever you want to take the double to the power of. Okay, and then here is an example of a method body that you might be given on an exam. You don't know what the while loop actually does, but you are given all of the information that you can use to determine it, right? You're given a result, you're given a factor x, a p left, which is equal to p, and then you're given updates, maintains, your loop invariant here. If you're asked what the loop invariant is, this is the loop invariant, and then you have some sort of progress metric, because we have to be sure that the while condition eventually terminates. If we don't have this decreases thing here, then what's to say that p left will stay positive forever and never be 0, and then the while loop will never terminate and Java will yell at you. Okay, so we're given the fact that result, factor, and p left might be updated. We're given the fact that the loop invariant is maintained such that p left is always greater than or equal to 0, and the second line of code here, which claims that result times factor to the power of p left is equal to x to the power of p, which, if you remember, is what we want at the end of the code. And then our, what's it called? Like updating factor or progress metric is the fact that p left will be decreased over time. Another thing we know, another piece of information that we can use to piece together the puzzle of what this while loop does is the fact that our while condition is that we are going to loop while p left is greater than 0. Okay, so here is what you will be given, and then you will be asked or tasked to use all of the information that you know to figure out what the value of the variables will be afterwards. So we have that x is equal to 3.0. We have that, can't see very well, P is equal to 5. Result is equal to 1.0. Have that factor is equal to 3.0. And P left is equal to 5. This is our starting state. And what we want to get to is the ending state, which is such that X is equal to 3.0 and P is equal to 5. And then we want to fill in what result is equal to, what factor is equal to, and finally what P left is equal to. Now, one of these variables on the right side, we can already fill in. And which of those variables is it? Why?
So it has to be 0.
It has to be, yeah. So the first part of that is that we are looping while P left is greater than 0. What is the second part? I'll scroll back up. There's one other part that proves, without a shadow of a doubt, that P left will eventually become 0. Yeah, that's one part. And then also, we maintain that P left is being decreased over time. So combining these two facts, or three facts even, which is that P left has to be greater than or equal to 0. So we know that it's going to be at least 0 to infinite max. Then we know that we're going to loop while P left is greater than 0. So technically, actually, it can only be 0. And we know that it'll eventually get to 0 because over time P left is decreased and P left starts at 5. So eventually P left is going to be 0. Okay, 1 down. Good to go. All right. Observation. P left is positive at the start of the loop body, and the loop body has to decrease it. How are certain ways that you could decrease P left? There's a million. You could divide it by 2. You could subtract 1 from it. You could subtract 1,000 from it every single time you go through the while loop. As long as P left is decreased over time, you are gravy. Okay. Idea 1 is to decrement P left. So we're making the assumption that the while loop is going to decrease P left throughout the loop. We don't know that this is the case, but we're simply using it as an example so that we can fill in the other 2 variables that we need to get. So the rest of the loop body, we have to maintain that the invariant is true, and these things must be true at the start of the while loop. So we need that P left is greater than or equal to 0. And that result times factor the power of left is equal to X of B. So we're highlighting the fact that P left has to be greater than or equal to 0. We know that this is true, and we know that P left has to be greater than 0 because of what we just talked about. The fact that P left, based on the while loop condition that we have, which is that P left is greater than 0, we know that this part of the loop invariant is always going to be true because when we start the loop, P left has to be greater than 0 because we just tested it in the while condition. So if we're drawing a picture, let me redraw the picture of the while loop. Something like that. Okay. So we knew that P left was greater than or equal to 0 before we entered the while loop, because otherwise we would have just left the while loop. And we know that it's true at the beginning because we didn't change P left during the condition. So we know that P left is greater than or equal to 0, and P left is greater than 0. At the end of the loop body, we know that P left minus 1 has to be greater than or equal to 0, because otherwise, when we started the loop, we knew that P left was greater than 0. So P left was 1 through integer.max. So this is what we knew was true about P left. That it was between the values of 1 and the maximum value of the integer. So we know that P left minus 1 has to be greater than or equal to 0 because the possible values that it can take on are 0 to integer.max minus 1. So these facts must be maintained, which means that we cannot change P left. P left is always going to be changed. So we know that's the case. Then since X and P do not change in the loop, why do we know that X and P do not change in the loop? It's based on some information that we are given. Anyone? Why do X and P not change? Yeah, because we're told that X and P do not change. Okay, so X and P must remain the same. So this is fixed in place. So in order to make this true, in order to make everything equal to 3 to the power of 5, we have to change these 3 values. So there is no updating of X and P because we know that they must stay the same. So what that means is that we need to update result from some initial value to some final value, somewhere in between here, in order to maintain the loop invariant, because we know that P left is being decreased over time. So we know that P left is being changed in this equation. So that's fixed in place. This is changed. And since that's changed, we know that we need to update either factor or either result in order to make sure that this remains the same. Because P left is being decreased, which means that result or factor must be increased in order to maintain the loop invariant. So we need to update result from result I to result F, and or update factor from factor I to factor F in order to make this true. Does it make sense why we need to do that? Raise your hand if not, otherwise forever hold your peace. Okay, yeah. I'll say it one more time. X to the P is fixed in place. We know this because the values of X and P were true, or were 3 and 5 at the beginning of the code, and we know that they were true. They were equal to 3 and 5 at the end of the code. They cannot change. This is fixed in place. We know that P left is decreased over time because it started at 5. The loop body was running while P left is greater than 0, and we are told specifically that it's decreased over time. That's our update metric. So we know that P left has to eventually be equal to 0. So this has to be changed as well. So in order to maintain the loop invariant, that this part of the expression, result times factor to the power of P left, is equal to X to the power of P, we have to either increase result or factor. And increase it from result I to result F, result initial to result F, final, and or update factor from factor I to factor F, where I and F are just initial and final. What's one way that you could do that? Well, one way that you could do that is set result equal to result times equals factor. So if you go through each iteration of the while loop and you test to make sure that this works, it does work. So let's erase things and then go through the example. So in the case that the decrement metric for P left is that P left is minus minus. Initially, when we start, we have that. Where's the thing? Where's the nice bit of code? Okay, so result times factor to the power of P left has to be equal to X to the P. X to the P, 3 to the 5th. What is 3 to the 5th? Can somebody do that real quick? Is it? I'll look it up. 243. It's a big number. Okay. So everything always must equal 243. It's always going to be equal to 243. So we have result is 1.0 times factor to the power. I'll write everything in. This is result factor the power of P left. And result is 1.0 at the beginning. Factor is 3.0. The power of P left, which is 5. Okay. Is this true? Is 1 times 3 to the power of 5 equal to 243, which is 3 to the power of 5? X to the power of P. Okay, I just looked it up. Is that true? Okay, good. Now, after the loop body ends, what we said that we were going to do is we were going to decrease P left. And the option that we were given is to update result times equals factor. So result 1.0 times equals factor is 3.0. So now we have that result is equal to 3.0. And then we have that 3.0 times 3.0 to the power of 4. Is that still equal to 243?
Yeah.
Yes, because we just took out one of the exponents, moved it to the front. So our loop invariant holds after the first condition, because we've decreased P left, we've updated result to be result times equals factor. And so we keep going. Now we have this gets decreased again, times equals factor, 9.0. It's 9.0 times 3 to the power of 3 equals to 243. It is. Just trust me. And then we decrease it again, 2. Now this becomes 27. Decrease it again. This becomes 1. This becomes 54. 84? 81? Okay. I failed a lot of math classes. And then this becomes 0. And this becomes, I know this one, 243. Okay, and now we say, oh my God, 0. That's our ending condition. P left is equal to 0. And what do we have? That's a 0. We have that result is equal to 243. Factor is equal to 3.0. P left is equal to 0. And the loop x to the power of p remains, as always, at 243. Is our loop invariant still holding? Is power there. 243 times 3.0 to the power of 0 equal to 243. Yes, so our loop invariant holds again. So now we have that result is equal to 243. Oh, factor is equal to 3.0. And P left is equal to 0. So without even knowing or making an assumption about what the while loop does, we were able to trace through the code and make sure that the loop invariant was maintained at every point throughout the process. Does that make sense? We were just making sure that the formula was correct every single time that we went through the loop. That's basically loop invariance as a concept. Okay, now you could do another thing, which is have P left. And in that case, you would have to come up with a different metric. We know that having P left would also work because at the beginning or before the while loop, we know that P left is greater than 0. Greater than 0. And so then we know at the start of the loop body that P left is greater than or equal to 0 because it was greater than 0. And then at the end of the for loop, we know that P left divided by 2 is going to be greater than or equal to 0 because the only values that P left could potentially be are 1 to integer dot max. And afterwards, they will be anywhere from 0 to integer max divided by t. So we know that at the end of the loop body, P left divided by 2 is going to be greater than or equal to 0. And then because of that, this fact must be maintained. So that result times factor to the power of P left divided by 2 is equal to x to the power of p. So again, we get back to the loop invariant problem, which is that we need to update result from result I to result F in order to maintain the loop invariant over time. How can you do that? Well, P left may be even or odd, but start with a simpler case where it is even. And what you will eventually get down to is the fast powering algorithm, where it's something like x to the power of p is equal to x to the power, or x times x to the p minus 1. X is I. And x to the power of p is also equal to x to the power of p divided by 2 squared. And you can go through and make sure that the loop invariant holds for that as well. And that's loop invariance. Only 20 slides today. But yes, given a loop invariant, given the condition of the while loop, and then given the update metric, which you are given, which in this case was that it decreases P left, you should be able to go from initial state to final state. Now, sometimes you can cheat because the method name will be called like divide by 2, and then you'll be given like x is 100. And then it'll ask you, they'll be like, what's the value of x at the end? So, well, it's 50, obviously. So you can sometimes get the answer and then work backwards. Like in this case, you could probably do 3 to the power of 5 and then get that the result was 243 and then work backwards to talk about what the loop invariant is and how the while loop may be updating the variables. But I'm not going to say that's cheating. That's just like a totally valid way to do things. Okay, questions, comments, concerns, confessions of guilt? All right, then we're done for today. If you have any questions, good luck studying on the final. You can Slack me if you have any questions. I know I owe some of you some great updates. Bear with me. I have a final today and then a few next week, but we'll get them in. We'll get them in. I'll see you all tomorrow for a review session. It's gonna be awesome.
Review session in here or the,
It'll just be in lab.
okay,
Yeah, I'll send out a reminder about that.
there a attendance code?
There is.